right, now we need to know how to go about selecting an analytical method for a particular analysis. Now, if we're not following some protocol or a particular procedure, we may find ourselves having to decide between using one method or technique to analyze a sample and another. And this may come down to equipment availability or the how accurate we need to know a sample. There are other outside factors that do come into play when we're selecting an analytical method. And this also allows us an opportunity to discuss some of these other analytical terms because they relate to selecting an analytical method. So, of course, we would like a very accurate analytical method. And the accuracy is actually defined as how close the experiment agrees with the true value or an expected result. Now, we say true value because actually we don't really know what the true value is, the actual value. Now you might say, well, if I weigh out a particular amount of sample, run an analysis on it, and then I get the result, I should actually know how much was in there because I weighed it out. Well, weighing something does introduce a small amount of error into the measurement. Those balances are not precise. They don't count down to the individual atoms. I suppose if it did, then you could have an actual true value, but they don't, and it's really just not practical to do so. So we just say we're going to get very close to the true value, but then we'll evaluate how well we know an answer using statistics and some error analysis. Anyway, that was a little bit of a detour just to say accuracy is trying to get very close to the true value. Now, precision is sometimes confused with accuracy because some people think that just because we have a very precise answer means that it is somehow accurate. That is not necessarily the case. They often go together, but they are separate quantities. Precision is a measure of the variability. It is uncertainty in measuring the signal. It is how easily can we reproduce the results. If we're having trouble reproducing the same result, that is an indication of poor precision. Now, we can have poor precision and still achieve accuracy, but it is a little bit harder and our accuracy will suffer as a result. We can have excellent precision but poor accuracy, and this could be something that comes down to even just the calibration of our equipment. Say we think a pipette is delivering 10 milliliters of sample, but instead it's delivering 9.8. Our results could be very precise, but there will be an accuracy problem because our pipette was not calibrated. All right, moving on to sensitivity. Sensitivity is the ability to establish that a change is significant. Now, what does that mean? It means that if I change the amount of analyte in our sample by a very minute quantity, that I will get a change that I can see in the signal. So if I change the amount of analyte by increase it by 1 nanogram, say, and then my signal goes up by a factor of 5. That is quite a sensitive method. And that's a good thing because that leads to lower detection limits. And lower detection limits are what we actually would like. We'd like to have a very extremely low detection limit so that this is the smallest amount of analyte that we can actually determine and say, yes, there's absolutely analyte there. And not just, well, it seems like there might be something there, but it's pretty noisy in the signal. If you've ever zoomed in on some spectroscopy, you'll notice that it usually fluctuates a little bit. This could also be illustrated by putting just an absolute speck of a compound on a balance that's only accurate to 0.01 grams. Well, that just will not detect it because it's below the detection limit. It won't register a number on the scale. So it's important to have very low detection limits. And another way to think about sensitivity is the slope of our calibration. So ways to increase the sensitivity would be to make a compound absorb more light by changing its chemical composition. One of the things that you may have done before is to take a copper solution and add ammonia to it, and it will take a very light blue solution and turn it into a very dark blue solution. The whole goal of that is to increase the sensitivity of the method, and that makes it a lot easier to detect small changes in copper concentration. Whereas if we didn't do that, the method would not be very sensitive. This also lowers the detection limit because a higher sensitivity will mean a lower detection limit. I'll probably try to draw a graph at some point to illustrate this. Now, specificity. We would like a method to be specific, that is, only respond to the analyte. So if we're doing a precipitation and we want to know how much of some quantity is there, we want to make sure that there are no interference in the sample. So an example of this could be bromine and chlorine. If we were trying to do a gravimetric analysis of these using silver, well, both will precipitate under those conditions. Both the bromine and the chlorine will precipitate. And so we would have interference. And in this case, it would be a positive interference because the mass would go up because both precipitate. It could also be the case where an interferent causes a negative interference. In the case of a gravimetric analysis, that would prevent the substance from reacting to precipitate in the solution. So it may grab on to the analyte and not let it interact with the precipitating agent, and then it would not be counted in the analysis, and then that would be a negative interferent. So we desire specific methods that only react with the analyte, but that's not always the case. Sometimes we have interferences. And this could either generate or change the signal from the analyte. It could enhance the signal by weighing more or absorbing more light at the same frequency that our analyte does, or it could enhance the signal. In that case, it could precipitate with the sample, and then we would think that we have a pure precipitate, but in fact we have interferent with it. Or it could fluoresce and give off light at that particular wavelength, and then it would lower the apparent amount of our substance in the sample. There's lots of ways that interferences can happen, including basically every method that we come up with could have some kind of interference. It's possible. Sometimes we have very specific methods, though. usually involving antibodies or something like that. Now, selectivity is a measure of how free a method is from interferences. So if we have a selective method that is, oh, this, while it does react with other species, or it does absorb light from this interference, it does so much less than it does for our analyte. So say we're doing atomic spectroscopy and we have some light being emitted from our analyte, and the light being emitted from that is some arbitrary units, say 10,000, and then we have an interferent that's emitting 5 of the same unit of light. Well, that interferent doesn't pose that much of a problem because it's quite a lot smaller than our analyte signal. So we may not have to concern ourselves too much with that. And that would be an example of a selective method. And of course, we can measure how selective a method is using the selectivity coefficient, which is just the response factor for the interferent divided by the response factor for the analyte. And again, these are just really the slopes, or when I was discussing the types of techniques, remember it was the signal equals some constant, and that's what these are, times the thing that we're measuring, the concentration or the number of grams, whatever it is, this is that proportionality constant. And so when we have an interferent, the signal is the proportionality constant of the interferent times, say, the concentration of the interferent plus the proportionality constant for the analyte times the concentration of the analyte. That would make up the signal. And to calculate the selectivity coefficient, we can just put these in to this particular equation. So that's a little overview on how analytical methods are selected. And again, sometimes this comes down to availability of the equipment, or whether that particular method can be easily adapted for that sample or that sample's matrix. In some cases, the matrix may cause a problem with a particular analytical method, but not another. So these are all things that we would have to consider when choosing an analytical method